Today, we're going to pull back the curtain on a concept that is so fundamental to computing, you literally use it dozens of times a day without even knowing it. We're talking about the stack data structure. I mean, really think about it for a second. You're clicking through websites, right? You go from one page to another, and then you hit back. It doesn't get lost. It takes you to the last page you were just on, and then the one before that, and the one before that. How on earth does it remember that perfect reverse order? Well, the secret behind that little piece of everyday magic is a data structure called the stack. And its entire identity, its whole reason for being, is built on one beautifully simple idea: last in, first out. This last in, first out rule, or LIFO as we call it, is the one and only rule of a stack. It's not a suggestion, it's the law. Whatever you put in last has to be the very first thing that comes out. And that strictness, well, that's what makes it so incredibly useful. Let's make this a bit more concrete. Okay, picture a stack of dinner plates in your kitchen. When you wash a clean plate, where do you put it? On the top, right? And when you need a plate for dinner, where do you grab it from? The top. You'd never try to yank a plate from the middle or the bottom. The whole thing would just crash down. And that, right there, is a stack. Simple as that. And this idea isn't some newfangled thing, not at all. It's been with us pretty much since the dawn of computing. We can trace its origins all the way back to Alan Turing in 1946. It was eventually formalized in the 60s and has since become absolutely essential for, well, everything from how your code runs to that undo button you can't live without. So how do we actually work with a stack? It all boils down to 3 core moves. The first one is push. Pushing is just the fancy term for adding a new item to the top. That's it. It's just like placing another clean plate onto the pile. Next up, we've got pop. Pop is the exact opposite of push. It's how you take something off the stack. And of course, it removes the topmost item. So the last thing you pushed on becomes the very first thing you pop off. That's our LIFO rule in action right there. And finally, there's peek. What if you just want to see what's on top of the stack without actually removing it? That's what peek is for. It lets you take a quick look at that top element, but you leave the stack totally untouched. Now, these 3 simple operations, push, pop, and peek, are what lead to the stack's most amazing feature: its unbelievable speed. In the world of computer science, we talk about efficiency using something called Big O notation. And let me tell you, the stack has a genuine superpower. It's called O of 1. O1. It stands for constant time. And in performance terms, this is pretty much the holy grail. All 3 of those operations, push, pop, and peek, are O1. So what does that actually mean for us? It means it doesn't matter one bit if your stack has 10 items in it or 10 million. Adding one more or taking one off the top is going to take the exact same ridiculously tiny amount of time. The size of the stack has 0 impact on the speed. It's instantaneous. So how is that even possible? It's all because we only ever care about one single spot: the top. Whether you build a stack with an array or a linked list, the computer always knows exactly where that top element is. It doesn't have to go searching through the entire collection to find it. And if you don't have to search, the action is immediate. It's that simple. Okay, so we've got this super simple, incredibly fast data structure. That's great in theory, but where do we actually see it in action? Turns out, once you start looking, you'll find stacks everywhere out in the wild. Ever heard of the call stack? That's what your computer uses to keep track of all the functions running in your code. That's a stack. The undo feature in your text editor? Yep, that's just a stack of all your previous actions. We already talked about your browser's back button. Seriously, from compiling code to solving a maze with backtracking, stacks are the unsung hero working behind the scenes. Now, that doesn't mean a stack is the answer to everything. To really get when to use it, you have to meet its sibling, the queue. A stack is LIFO, last in, first out, like our plates. A queue is FIFO, first in, first out. Just think of a line at the grocery store. The first person who got in line is the first person who gets to check out. So if you need to process things in the order they showed up, you want a queue, not a stack. All right, now that we've got the what, the why, and the how, let's have a little fun and put this knowledge to the test with a classic challenge. This problem, valid parentheses, is a favorite in coding interviews. The goal is simple. Check if a string of brackets is properly matched up, and the solution is a perfect showcase for a stack. Here's how it works. You go through the string, and every time you see an opening bracket, like open, open, or open, you push it onto the stack.
The moment you see a closing bracket, you pop the top element from your stack and check, do they match? If they do, you keep going. If they don't, or if the stack was empty, you know the string is invalid. It's a really elegant solution, and it's powered entirely by that LIFO principle. So, from a simple pile of plates to the backbone of complex software, the stack is just an amazing example of how powerful a simple constraint can be. That strict LIFO rule isn't a limitation, it's its greatest strength. So the real question now is for you. Knowing how it works, what will you build with it?